Hello everyone, I wish that you're all doing great. In this video, I'm going to derive the expression for logarithmic decrement of a single degrees of freedom damped free vibratory system. You can see that system here, and there is the governing differential equation. Now, if you solve this governing differential equation for an oscillatory system, when I say for an oscillatory system, the damping factor zeta, that is going to be less than 1. I'm going to pronounce this time this notation as zeta. So whether I pronounce that as zeta or eta, sometimes I use them interchangeably. Please excuse me, forgive my ignorance. Okay, where this damping factor, which is the ratio of the damping coefficient to the critical damping coefficient, if it is less than 1, then the system is going to oscillate. Now, if you solve this governing differential equation for that particular case, the response that you are going to get, that is the displacement of mass at any instant of time, you see this mass is going to move to and fro like this, and the displacement of the mass at any instant of time is given by capital X into e raised to the power minus zeta omega n into t into sine omega d, which stands for the damping frequency in radians per second, omega dt plus phi. So that is the equation. Now, if you're wondering, if you're mystified, if it's very mystical, what you can actually do is you can watch the part 1, part 2, part 3. You can choose which part you want to watch. It's completely at your discretion. That can actually demystify if you are wondering how this particular equation is coming in the first place. Okay. Now, I'm going to draw a graph that represents the displacement of the mass at any instant of time. Of course, it's going to be an oscillatory system. So what happens here, the mass, if you plot the displacement along the y-axis and the time along the x-axis, then because it is an oscillatory system, you start with a higher amplitude, and as time goes by, the amplitude of vibration gradually decreases. Well, I should not be using the word gradually decreases, but rather I have to say the amplitude actually decays exponentially. Okay, suppose you start with an amplitude x naught. After one complete cycle, the amplitude is going to be x1. After 2 complete cycles, it will be x2, then x3, then x4, so on and so forth, right? Now, this amplitude is going to decay exponentially. I will explain that in a minute. You see, the amplitude is decaying. The amplitude of the sine wave is decaying exponentially. For obvious reasons, you look here. This is going to be a sinusoidal response. You are going to get a sinusoidal response. And you see, this can be considered as the amplitude, capital X, which can be considered as the amplitude of the sine wave. Yes, definitely, that's the amplitude of the sine wave. And what happens when you hit a sine wave with an exponential term that is sitting here? When you hit a sine wave with an exponential term, still you are going to get a sine wave, but you are going to get an exponentially decaying sine wave. The reason is because the exponential term is raised to the power of negative. So you are actually going to get an exponentially decaying term. Okay, now let me write what would be the response at the initial time. At time t naught, what is going to be the response? Let us say that at time t naught, what is going to be the amplitude? That is quite axiomatic, obvious. So at t naught, the value of x will be x at t naught, that is going to be x naught, and that is equal to capital X into e raised to the power minus zeta omega n into t suffix naught, because that indicates that it is an initial condition at time t naught. And because you are talking about the amplitude, which means that it should be the maximum, the value of x should be maximum. And you see, the value of x becomes maximum when this term and the sine term becomes maximum. And what is the maximum value of sine? Well, the maximum value of sine will be 1. So that becomes 1. So you're going to get an equation like this. Let me call this equation number 1. Now what happens after one complete cycle? What is going to be the response after one complete cycle? That is, at time t1, the value of amplitude is going to be x1, and that is equal to capital X into e raised to the power minus zeta omega n into t1. So that's going to be the equation for the amplitude. Maybe I can call this equation number 2. Right. So now I have an equation that is x0. I can have an equation at x1. Then what is the maximum amplitude? x2, x3, x4, so on and so forth. All I'm going to do is divide equation number 1 and 2. So I'm going to get the ratio of the amplitudes. So I'm going to say x0 by x1. So what is that you're going to get if you divide equation number 1 by equation number 2? So you are going to divide the two equations, x0 by x1. Immediately, this x is going to go away. X in the numerator, x in the denominator cancels each other out. And you see, this equation 1 and 2 is of the form e power minus a divided by e power minus b. What is e power minus a over e power minus b? That can be written as e power minus a into e power plus b. And that can be written as e power minus a plus b. That's right. I'm going to pull exactly the same technique here. Okay. So if you pull exactly the same technique, you are going to get x0 divided by x1. And that will be equal to e raised to the power minus a. What is in place of a? Minus psi omega n t naught. So I'm going to write minus psi zeta omega n into t naught plus zeta omega n into t1. Am I correct? I think that's right. Okay, now in the next step I can pull zeta into omega n. These two terms are common. I can pull them outside, so I'm going to get x0 over x1. That is equal to e raised to the power, pull the common terms outside, minus zeta into omega n into t naught. Because I'm taking the minus sign outside, I'll be getting t naught minus t1. Or if I bring the minus sign inside, I should be getting t1 minus t naught. So, well, I will do one more step. It's going to be t naught minus t1. Obviously, this t naught minus t1, you see, t1 is going to be greater than t naught. So that term is going to be negative. This will be negative. Outside you have got a negative, so you are going to get negative into negative as positive, right? That's correct. So I can simply say, by pulling the negative sign outside, I can rewrite this equation as x0 over x1 is equal to e raised to the power zeta into omega n into t1 minus t naught. And please tell me, what is t1 minus t naught? It is the time duration between the cycles. It is the time required for one complete cycle. That is what t1 minus t naught actually is. And the time required for one complete cycle is inverse of the damped frequency, because this is a damped system, so that should be the inverse of the damped frequency. So in the next page I'm going to write just that. So x0 over x1 is equal to e raised to the power zeta omega n into t1 minus t naught, and that t1 minus t naught is just the inverse of the damped frequency. So I hope that is fine with everyone. So I don't want this exponential term to be accompanying us. So what I'm going to do is I'm going to undo the exponential function. So let me take the natural logarithm on both sides. So I'm going to get natural logarithm of x0 over x1 is equal to zeta into omega n divided by the damped frequency. But we have with us the damped frequency is simply the damped frequency in radians per second divided by 2 pi. So plugging that value is going to give us the natural logarithm of x naught over x1 is equal to zeta into omega n divided by omega d divided by 2 pi. So in the next step, I'm going to take this 2 pi to the numerator. And also I have an equation for omega d, which is square root of 1 minus zeta square into omega n. All these concepts are derived in part 2 and part 3. You may want to check that. So the natural logarithm of x naught over x1 is equal to 2 pi zeta divided by square root of 1 minus zeta square. Well, I missed this omega n in the numerator, and there is an omega n in the denominator. Omega n in the numerator and omega n in the denominator, they cancel each other out. So the finally the expression, the natural logarithm of x naught over x1 is equal to 2 pi zeta over square root of 1 minus zeta square. I'm going to put a box there. This is the expression for the logarithmic decrement. Okay, now how do you think this expression is going to be useful? The first thing that I have to tell you is, you see that the logarithmic expression is going to be tremendously useful because the value of damping coefficient is just going to be constant. And if the value of damping coefficient is just going to be constant, then x naught, not only ln of x naught over x1 is going to be the constant, but ln of x1 by x2 is also going to give you the same value. Natural logarithm of x2 over x3 is also going to give you the same value, so on and so forth. Okay, suppose you are designing an automobile. Say for example you are designing a car, and maybe there is a bump and your car wants to take over this bump. When the car is moving over this bump, then maybe the amplitude, the initial amplitude, maybe, for example, I'm saying x naught maybe 8 centimeter, and you want that immediately in the next cycle, you want that to be dropped to 0.5 centimeter. Now, if you want to design such a system like that, right, then you can find out what is x naught by x1 and take the natural logarithm. If you know that, you can easily find out what is the damping factor. For your particular system, you can easily find the damping factor. So that is one of the reasons why we actually are interested in logarithmic decrement.